Okay, I think we'll get started. Good morning, everyone, or good evening, or good afternoon, wherever you are. This is the one of the final sessions and one of the most interesting sessions of the Brown AI Winter School, and we're going to talk about data compression for LUX-ZEPLIN. And let's talk about what that actually means. Let's just dive right into it. So, in the beginning, the universe, the cosmos created this stuff. Technically, what you see here is not the beginning, right? This stars and galaxies were created a little bit after the Big Bang, quite a bit after the Big Bang. But the stuff that made that was around earlier. And it turns out we don't know what all of that stuff is. So if we look at the energy content of the universe today, what we've measured today, what we see ourselves, the trees, desk, your dog, whatever. It's about 4.6%. Everything that you see, most stuff that you see, 4.6% atoms, baryons. 24% is dark matter, and about 71% is dark energy. And why do we call them dark? Um, and today specifically we'll focus on dark matter. That's our focus today. But I want to just quickly talk about the word dark. So dark means we don't know what it is, but we can still infer its existence. So dark energy from the accelerating expansion of the universe, and dark matter, what our experiment LUX-ZEPLIN is set up to study, is inferred, the existence of dark matter is inferred another way. So one of the most commonly discussed measurements is galaxy rotation curves. So I took this very nice image from this website down here. But the figure on the left, on the y-axis, is the velocity in kilometers per second, and the x-axis is r in kiloparsecs. And what does this mean? So in galaxies, if you just look at galaxies, the velocity as a function of distance from the center by naive Newtonian gravity should fall off with distance. All right, if you just do the calculation. I just make that sound simple, but there's a lot of technical details that go into measurements. But it doesn't fall off as distance. The velocity does not fall off as distance. So from these galaxy rotation curves, we can infer that there is more mass in the galaxy than the luminous matter would indicate. And so this is a specific curve from this galaxy NGC 3198, taken from this measurement here. So if we look at galaxies and we look at stuff that's moving within the moving within the galaxies, we would expect that the velocity of those things would fall off as distance from the galaxy center. But it doesn't. It's kind of does this plateauy thing here, right? And again, this kind of tells us that there's more stuff inside the galaxy than we can actually see with any telescope. Stuff that doesn't interact, stuff that doesn't give off light, right? Things that don't give off light and we don't know what they are, we call them dark. So in this case, this is dark matter. Dark energy is a completely separate topic. You can talk to somebody else about that at some other time. But today we want to figure out what's causing things like this. There are other measurements that help us infer the existence of dark matter, but that's a in-depth topic and a very interesting topic. I implore you to go and research it. It's one of the biggest open questions in physics, in any field of physics today, and it's unsolved. So why do we get these measurements that tell us there's more stuff in the universe than there actually is? And how do we go about finding out what that stuff is? So just to recap, the universe is made up of normal matter, mostly what you see around you, like your water bottle. There's dark energy, which we don't know what it is, and then there's dark matter, which we can infer from astrophysical measurements that we don't know what it is. So today we're focusing on excuse me, the detection of dark matter. And there are several hypotheses of what dark matter is. Dark matter is kind of a catch-all term that just says there's matter or something, we don't know what it is. Hence it's dark. So a couple of hypotheses. One, it could be a new type of particle or particles, depends on what model you're looking at. Or it could be some sort of modified or new theory of gravity. But most physicists rather, like the idea of a new type of particle because uh, positing these hypotheses has worked out well in the past. Positing new types of particles has helped us solve physics problems in the past, and we've discovered new particles in the field of particle physics by positing these hypothetical particles and searching for them. So this is a well-motivated idea. And so a few ideas about what these particles might be. There's something called a weakly interacting massive particle, or WIMP. Weakly mean weakly meaning it doesn't really interact with anything except the weak force and gravity. And there are other things called axions or axion-like particles, which are outside of the scope, but they're other candidates. These are other candidates, and there's a bunch of others. But today we're going to focus on WIMPs. That doesn't mean that. Just don't worry about the acronym. Just know that they're called weakly interacting massive particles. Yeah, like I said, they don't interact with anything other than gravity and the weak force, supposedly. But if they interact only with, with such, if they only interact weakly, how do we directly detect them? I mean, if they interact weakly, then they're not going to interact with you or me or any sort of matter very often. It's very hard to detect if they exist. So we use a giant vat of liquid to detect them. It sounds silly, but I promise you, it's not. It's actually quite a sophisticated and ingenious way of doing things. Specifically, we're going to use liquid xenon, a giant vat of liquid xenon, to try and detect these hypothetical WIMPs. And there's a lab for it in the United States at the Sanford Underground Research Facility in South Dakota. There's a detector called, this is an older picture, it's LUX, but now it's upgraded to LUX-ZEPLIN. It's about 4,850 feet underground, which is about 4,300 meter water equivalent rock. You put it underground to shield from cosmic backgrounds coming from space that might interact with the detector and swamp out your signal. So if there's dark matter and there's other stuff, you want to hide the detector from the other stuff. That's why we put it underground. So we bury the detector way underground for a clean-ish environment. And so the current iteration of the detector is this LUX-ZEPLIN experiment. You can see the entire name for it up here. I won't read it out loud, but it's this giant experiment, this giant vat of liquid. And the idea is hopefully that the dark matter will come in and then knock into one of the xenon atoms inside this detector. And it will produce a signal, a very distinct signal, which we can use to say, aha, we've got a dark matter candidate. But how does that actually work? If a WIMP or some dark matter candidate comes in, knocks one of the xenons, and produces some sort of signal, well, that sounds simple, but what does that actually look like? So just to give some numbers, there's about 7 tons of liquid xenon, 2 ton liquid xenon for a photon gamma tagger, and a 17-ton gadolinium doped liquid scintillator for neutron backgrounds. If that's a lot, don't worry. Just know that it's a giant vat of liquid xenon, and we want dark matter to come and hit that xenon and give us some sort of signal. So this is how it works, right? So you've got a particle coming in, it knocks one of the atoms, and it leaves. It initially produces a prompt UV photon here, and then there's some ionized electrons that drift up an electric field, and then it produces a delayed signal up here. So the prompt signal is called S1, and the delayed signal is called S2. And these electrons are drifted by an applied electric field. And when you have this chamber that drifts the electrons in an applied electric field, this is called a time projection chamber. Time projection chambers are actually a very, very important tool in particle physics. It's not these types of detectors are not only used in dark matter searches, but you can use them in many other things. For example, in high energy physics experiments, they're used for background background monitoring. So time projection chambers are one of the most important tools in all of particle physics. And this one is a very big and very, very sophisticated one that is incredibly sensitive to very, very small signals. Okay? And so the time interval between this S1 and S2 signal, remember the S1 is the prompt signal, and then the S2 is the delayed signal. The time interval between them gives you the depth of where this happened in Z. Okay, this is this direction is Z. So the signals come from if a WIMP comes and scatters off the nucleons, right? Not the electrons. So we want nuclear recoils, WIMP nuclear recoils. And generally we think because they interact so weakly, WIMPs scatter only once. If we can detect something that scatters multiple times, i.e. multiscatter, then we know it's a background and we can reject it and we're good. So we want to have these types of signals here. Every time we see these signals, this S1 and S2 signal, we can tell whether one, whether it's a single or multiscatter, and whether the recoil came from a nuclear recoil or an electronic recoil. So these things help distinguish between your WIMP signals and other things. And they're detected, and there's these little colored circles up here. We're going to get to what these mean in a sec. So just to put a finer point on it, so a particle comes in, bang, S1, photons, some electrons get get freed, and they're drifted in this applied electric field up here. They come into this gas phase, which is up here. So you've got some liquid xenon here, then gas here. These produce light. The light is collected up top here. So the S1 signal is produced here. It's a tinier signal. And then the S2, this large signal here. And the time difference between these can give you the depth in the detector. Okay, but what are these things? These arrays of circles? Well, they're photomultiplier tubes, i.e. PMTs. The PMTs, the PMTs are light collectors. Just put it simply, light collectors. They're very, very sophisticated light collectors, but what they do is they detect light in an incredibly sensitive way. And I encourage you all to just pay attention to the references down at the bottom of the slides if you want more info and other stuff. So we call let's say one circle is one PMT. There are more here than I'm showing in this figure, which you'll see in a sec, but let's just call one circle one PMT. So one PMT is equal to one channel. I just want you to hold this nomenclature in your mind here. So we have an array of photomultiplier tubes that detect these S1 and S2 signals that come from WIMP interactions in the detector. And what we can do is we can reconstruct the light, we can reconstruct the signal from the light detected by these photomultiplier tubes. All right, the photomultiplier tubes send the signals that it produces to the electronics where the data is stored. So WIMP comes in, bang, S1 signal, S2 signal, light is collected in the PMTs. The PMTs send the signals to the electronics record the data, and it's a lot of data. All right, so here's an actual PMT array. Brown is very, very much involved in this. So this is Brown is a premier institute for this type of work, but this is actually what it looks like. So each one of these kind of amber colored circles, that is one PMT. And what does one PMT look like? Well, you can see these here. So the light is collected in this front face here, something goes in, and it comes out in the back, recorded by the detector electronics. The detector electronics stores these data. These data are then analyzed by the physicists to try and separate out, WIMP signals from not WIMP signals. And there's a lot of other interesting physics that goes on within LUX-ZEPLIN as well, not just WIMP searches, but that's beyond the scope today. So these incredibly sensitive photomultiplier tubes inside this incredibly sensitive dark matter direct detection experiment can give you dark matter information and information on a lot of other physics. It's very, very sensitive and a very interesting experiment. But note that these are the PMTs, okay? So data from these are what we are going to focus on today. So data from the PMTs are recorded by the readout electronics. The data is stored on the disk for further analysis. But there is a large quantity of data, about 1 petabyte per year. That's a lot. Okay. Not all of the data or other features of the data are necessarily useful in doing physics searches, WIMP searches. right? So can we reduce the amount of data that is saved and still perform high fidelity physics searches? In other words, can we reduce the data such that we store less of it, but are still able to produce very sensitive physics searches? And that's the question we're going to talk about today. And the answer is yes. I'm just going to give you the answer. The answer is yes. We can. We do seem to be able to do that. And we do that through machine learning to compress the data. Hopefully you all know what data compression is, and we're all in the 21st century on a computer. Hopefully you know I don't need to explain this. But maybe what you don't know is that you can use machine learning to do data compression. And that is very interesting. Not only is it very interesting, it's very widely applicable. So the techniques you're going to learn today that are being applied to LUX-ZEPLIN, you can take them and use them in other places. All right, so this is a very useful technique. So the model we want to use, the architecture we want to use to do this data compression is called an autoencoder. And so I'm just going to stop there, and I'm going to hand it off to our very talented undergraduate researcher, Woody Hulse. And he's going to share his screen. He's going to talk about the data first, and then it's going to flip back to me. So I will stop share now.
Hello, everyone. So I'll have you turn your attention to the notebook, the Google Colab notebook, which is in the Google Drive under Module 6. And while I'm talking, you should be able to see my screen now. You can go ahead and run these first few sections, mounting your Google Drive. If you've been in previous sections, this will be pretty familiar for what you've already done. So as Shawn talked about, we are using this LUX-ZEPLIN data, and specifically the motivation for this, as we mentioned, we have petabyte scales of data. That's like a quadrillion bytes, and almost impossible to work with certainly on a personal computer. Even on large scale computers, it's very difficult to do. And so we want some way to take this large quantity of data and shrink it into some workable form. And there's different techniques to do this. There's which are generally referred to as compression methods. There's lossless compression methods, basically meaning that there's no reduction in the actual information encoded in the data, and lossy compression methods. Of course, lossless compression methods, being that they are a perfect compression of data, are quote unquote better, but they can often only get you so far in terms of the amount that they're actually able to reduce the data. So that they're not going to be the focus of what we're talking about here today. We're specifically talking about this type of lossy data compression, and specifically using machine learning to achieve lossy data compression. So for lossy data compression, we have some trade-off between the amount that we reduce the size of the data and the amount of information that we preserve in the data. And so I keep throwing around what the term the data. Let's talk about what that data actually is. So we're using LUX-ZEPLIN data. Actually, we're using simulated LUX-ZEPLIN data. And what I mean by that is we've taken a pretty accurate simulation of what goes on in this detector and simulated for an 8x8 photomultiplier tube array. And so we have about 10,000 events of simulated data that we are going to be using today, because obviously we can't work with a huge quantity. And even for the data that we have from LUX-ZEPLIN, those are for the 492 channels of PMT array data. And so that's a little bit difficult to work with for the purposes of this workshop. So with this 8x8 PMT array, we're looking specifically at multi-scatter events. So as Shawn mentioned, these are events where a particle comes into this huge liquid xenon chamber, collides with one liquid xenon particle, bounces off, hits another liquid xenon particle. They both scintillate light, or they first percolate electrons up into the chamber and scintillate light into the PMT array. And so if you run this event GIF block, we can kind of see what an example of this looks like. So you have the first collision that happens, which scintillates light, and then the second collision that happens shortly after. So again, we have 10,000 events of this data. And in terms of the amount of like numbers that we need to store it, there's it's an 8x8 channel array with 700 time steps, which goes out to 44,000 floating point numbers per each event, or 179 kilobytes. And for data that is in the experiment being collected at nanosecond scales extremely frequently, while that may be workable for what we have today, for larger scales, you can imagine that this is very difficult to work with. So to give you an idea about the actual size of the data, you can run this block and see that, okay, even just the 10,000 events, which is not very many, that we have here in the simulated example, that is 1.79 gigabytes consumed on disk. And so the goal of this exercise is going to be to figure out how to reduce that while maintaining the quality of the data. So then the other question is, okay, how do we maintain the quality of data? And that's through this delta mu prediction task. So what we're going to do is we're going to say, all right, in order to assess the information encoded in this data, let's use this data to perform some auxiliary task on some baseline network that we know how it performs, and then see how that performs on the raw data versus the compressed data. And the difference in performance is going to be basically how we evaluate how well our model compressed this data. So we can go ahead and plot what we're plot this this summed events plot, which is going to show a little bit better what we're trying to predict here. Basically, again, we have two scatters that are occurring in this chamber, and both of them look vaguely Gaussian, and we want to figure out, okay, what is the difference in time, or the Gaussian centers, really, between these two events, which is denoted by these red lines. So if you were present for module 1, this will be pretty familiar to you. We're going to use similar techniques and a similar neural network to perform this task, as you may have done for module 1 and the single scatter versus multi-scatter, or maybe it was the intro module, single scatter versus multi-scatter prediction task. So like all machine learning, we have to first split data into train and test sets. So we'll do an 80-20 train test split, 80% of the data in our training data and 20% in testing data, which we're going to set aside. And we'll go ahead and this model should already be filled in for you. It's just a simple multi-layer perceptron. Again, it should look very familiar to previous neural networks that you may have seen in this workshop. So you can go ahead and run this block, and it'll train a neural network for you on this raw 8x8 data to try to figure out, okay, what is the difference between each scatter and a multi-scatter event for each of these 8,000 train events. So this should take maybe a couple minutes to run. You shouldn't need any CPU help or GPU for help for the purposes of this or any point later in this workshop. And you should be able to see that loss is decreasing, validation loss is decreasing as well. You might see validation loss increase at some point, and we can talk about that a little bit later, but as you can kind of see here, validation loss takes a jump. That's because of a couple of reasons, namely because we don't have very many events that we're training on. And so what the neural network has been able to do here is memorize the training data and use that information while training, which on this validation data set is not as effective, of course, because it's a different set of data, which this phenomenon is called overfitting. And so after this trains, we'll get a final testing loss number. And this is, again, our baseline, just an idea of how good this initial raw data is in performing this task. And we also get training time, which we'll also want to keep in mind as well. One thing about data that's smaller is it's also faster. So computation that's performed on the data can be done much quicker than if it's just raw, much larger data. Um, and so we can kind of visualize this in the following plot, where we see the predicted versus true delta mu plotted against one another. And you can kind of see, hopefully you'll see a positive linear correlation, which basically says, okay, for the higher delta mu events, for the events, in other words, where these two red lines are further apart, the neural network should correctly predict higher delta mu, and vice versa. For lower true delta mu, it should predict less true delta mu. So before we dive into autoencoders, I'll hand it back to Shawn, who will talk a little bit more about what exactly an autoencoder is.
Yes, so I'm going to talk about briefly what an autoencoder is, this specific type of model architecture that we're going to be using for the data compression. So an autoencoder is a autoencoders are types of artificial neural networks. To remember what you learn about artificial neural networks versus biological neural networks from the introduction module. So the autoencoders are types of artificial neural networks that perform an unsupervised learning task to learn representations of the data, called a latent representation. All right? Keep that word in mind, latent. So this latent space that the neural network learns typically has a lower dimensionality of the original data. And because it's lower dimensionality, we can get data compression. How does it do? How does it actually learn, right? So it learns by trying to copy, excuse me, the input to the output, right? And in other words, it tries to learn the identity function. Hopefully everyone is familiar with this identity is, right? But it has to be done under certain constraints. For example, forcing the latent space to be of a smaller dimension than the original data, or adding some noise. So it forces the model to learn efficient representations of the data. Right, that's the key. Learning efficient representations of the data. Hopefully, it learns things that are important, and that can be used to reconstruct the original data and still provide you useful information, and in this case, to perform physics searches, right? So remember, we're talking about latent space, latent representations that typically have a lower dimensionality. That is the key here. So autoencoders are composed of two parts, the encoder and the decoder. Okay? And you can see this is from Wikipedia. So you have an input layer, which is the encoder, some compressed, let's call it compressed space here, and then the decoder layer, which tries to do the reconstruction. So that's really all it is, just these two parts. Right? Conceptually, it's very simple. You would think, well, can it actually do what we're telling you it does, compress the data? Turns out, yes, it can. This is conceptually very simple, and in practice, very powerful, very useful, and like I said, very generally applicable. So how do we apply these autoencoders to the LZ channel data? So remember I said these PMTs are the things that we were calling the channels. And the data from each one of those are stored on disk, right? So the PMTs collect the light, they store it on disk. And we want to use autoencoders to, excuse me, compress that. So, as stated previously, LUX-ZEPLIN produces copious amounts of data, not all of which are necessary for physics analysis, that search for dark matter signals. I'll just reiterate this plot here. We want to compress the data obtained from the PMTs. And today we're using, I believe we're using simulated data. But we want to compress what comes out of these guys and still have a faithful enough representation of the data after it goes to the autoencoder, after it comes out of the decoder part of the autoencoder, and still be able to do a physics search for WIMPs or whatever you're searching for. So, and if we can do this successfully, then we've demonstrated a technique that can be used to efficiently store data on disk. This reduces the costs of data storage while still providing enough information to do a dark matter search. And again, this is a very powerful and very generally applicable technique, but it is particularly important here because we collect a lot of data. And particle physics in general collects a lot of data. And we really, really want to only keep what we think is important for the discovery of new physics, physics beyond the standard model of particle physics, or beyond the standard model of cosmology. So that's basically the idea, right? We want to take the data from the PMT array and we want to compress it using autoencoders. So just to summarize, we've got stuff that we don't know, we have no idea about, dark matter. We hypothesize it's a particle. The particle comes in, collides with the detector. That collision produces some signal. The signal is collected by the PMT array. The PMT array sends the signals to the electronics. The electronics store it on disk. And we want to use autoencoders to compress that data that's stored on disk to do things more efficiently. So that's basically the summary, right? We have some astrophysical phenomena, such as seen in galaxy rotation curves of unknown origin. We call it dark matter, just because we don't know what it is. We hypothesize a new class of particle called a WIMP. There are others, but WIMPs are one of the more common, more accepted hypotheses to search for. We built a large liquid xenon detector to try and detect these particles coming presumably from outer space. They collide in our detector. We collect that data in the form of photons through the photomultiplier tubes. And we want to use machine learning, specifically autoencoders, to compress the detector data that's collected through these PMTs to perform an efficient dark matter search. So efficient in terms of storage costs, in terms of data analysis efficiency. If you've got a lot of background, a lot of unnecessary stuff that you got to get rid of, it takes longer. And this technique that we're using for compression is generally applicable. This use of autoencoders to compress data is generally applicable. So you can use it for different problems in physics and outside of physics. Okay, and that's what I wanted to say. Please type questions in the Q&A if you have any. Otherwise, I'm going to stop share and hand it off back to my colleague Woody.
We can start the hands-on portion of the workshop. And so you should see right under the code block that we last ran, information about autoencoders and this autoencoder block. And so this is the part of the workshop that you get to sort of chart your own path on, where we have you have the ability to specify the hyperparameters for the autoencoder itself. Again, basically what we have here is two MLPs, an encoder that translates from the input into a latent space, and a decoder that translates back from the latent space into the output, which should be an identity mapping from the input, or as close to it as possible. And so you'll have the opportunity to define whatever hyperparameters, dense layer sizes that you'd like. If you want to try using non-dense layers such as convolution, they can be suited for this task. But sticking to dense layers is completely fine. Activation functions as well. If you've seen them from previous workshops, that's great. You can use most of those. Just be mindful about the space that we're working in. For the data itself, it's not normalized. So from negative numbers to all positive numbers. So keep that in mind when designating activation functions. I guess the output activation is already set to linear, so you shouldn't need to worry about that. And then you shouldn't also need to, for now, worry about the variational autoencoder. That's kind of extra, and if you're curious, but by all means, if you do want to take a look at that, it's a little bit extra. You can also specify the latent size. This is a variable that's referenced here as the kind of end of the encoder block. This does a lot of work here. This is basically saying what the size of your encoded representation is. And so if you remember from earlier, we have a 44,000 vector size of the input. That's our 8 by 8 by 700 input data. And so the latent size you specify here is going to determine the degree to which we're reducing that data. So I'll come back with some examples of potential inputs. Again, as Shawn mentioned, if you have any questions, this is a good time to ask them in the Q&A section on the bottom of the Zoom.
There is one request I've had, which is I think because of the screens people are watching on, if you can make your font or blow it up a bit so that they can see it more easily, that would be fantastic.
Yeah, how's that?
Yeah, even one more if you're willing. But don't make it ugly. Thank you, sir.
Yeah, no worries. Okay, so again, you can specify whichever parameters you'd like. I can show some example parameters that might make sense. Again, we're creating an MLP that's reducing gradually the size of the data. And so you might define dense sizes that slightly decrease into the latent size. So we could say this goes from the input shape, the input size to 256 to 144 down to the latent size, and then back up to 256 and then to the input shape size again, which should already be filled in for you. In terms of activation functions that make sense, I would recommend sticking with linear activation for the latent space, although again, any activation should be fine. For these activations, for the interiority activations, it can really be anything. I'll go with ReLU, which is a very common activation function used in machine learning because it's very fast, it's a very quick function to compute. Basically, it's 0 for any input less than 0, and the input itself for any input greater than or equal to 0. So you can go ahead and run this block. And we can also specify latent size. I'll start off with 128. So that would be roughly a 300-fold decrease from the 44,000 that we started with as the data size. For the loss function, we're looking for a loss function that can determine the magnitude of the difference between the input and the output. That is, we want the reconstruction output to be as close to the input as possible. And again, the input and output are not normalized. So you want to choose an activation function like mean squared error that can operate on the entire real number plane. And optimizer, again, this is mostly down to preference. I find that the atom optimizer works best in a lot of these circumstances. But again, you can check, there's documentation linked here. So I highly recommend looking through this documentation, trying to put together models that might make sense, running them through the rest of this exercise, and then revisiting and seeing how you can change the model, what changes that you make affect the performance of the model, the speed at which it computes, as well as the loss, the reconstruction loss that you get. So we can, running this block, you should be able to see a summary of the model that you've created. In this case, we have a 23 million parameter model, which is quite large. If you're making only an MLP, it isn't too large to be able to compute on the CPU for this notebook. But we can train it. It should be set to 5 epochs. That should be enough to almost converge, at least, to the model to a reasonable solution of the reconstruction. And it'll take a couple minutes, depending on whatever hyperparameters you've chosen. So here I'll actually, to speed it up, the bottleneck layer here is often the input to this first density. We can reduce that size just to kind of speed things up a little bit here for the purposes of demonstration. But again, feel free to choose whichever parameters you think make sense. So this should run quite a bit faster. And again, here, this loss figure is currently the mean squared error, or the average of all of the squared errors between this 8x8x700 grid input and the result taken from when we pass this input through the encoder, through the decoder block, and get an input at the, or get an output at the end, which should be as close to the input as possible. So while we're doing this, I'll explain a little bit more what the point is, why we're doing all this, maybe why this works in the first place. The idea is here, from passing the input through this network, getting an exact copy from the output, each individual layer has no prior information other than the data being passed directly into it from the preceding layer. And so as information moves through this network, it's forced to take up smaller and smaller sizes. And because we ultimately reconstruct it to the same size as the output, as gradients flow backward through the network optimizes to make this information as complete as possible. And because this information is dependent on this information, it also refines the quality of the data here, which also necessitates refining the quality of the data here, and et cetera, et cetera. So it ends up being the case that at each layer, we have as complete of a data picture as you can fit into that layer, or at least that's what we're optimizing for in each. And so this central layer, this layer after the encoded, or at the encoded portion, what we call the latent space of the autoencoder, ends up containing all of the quote unquote information, or at least most of the quote unquote information, as is needed to reconstruct the input. And again, it's most of the information. So we don't have an exact reconstruction. We have as close to a reconstruction as possible, meaning that there's some data that's being lost. If this were a truly lossless data compression method, this final loss here would be 0. But the fact that it's not a perfect reconstruction says, okay, we're losing some information here. So hopefully you've had a chance to create something similar to the network I've put together here. We can run through now and see how much information we've lost. Specifically, we can run this plot to see, at least visually, what this reconstruction exactly looks like with respect to the input. So you'll remember the plot earlier that we had, the GIF earlier, that we could visualize what is this, what do each of these events look like. What we can do is take an event and pass it through the encoder, pass it through the decoder, and see in the same visualization code what this would look like side by side. Again, our goal is to see this reconstruction look as close to the input as possible. So we'll see here in a second how well our network did. So again, the reconstruction on the right, the true hit pattern on the left, you can see that the behavior is roughly translated from the left to the right. So we get some weird artifacts here, some extraneous noise. Maybe this is a little bit smoother than this is. And again, this is due to the fact that we don't have a perfect reconstruction of the original input. But it looks pretty reasonable, at least in my opinion, for what the input data looked like to start out with. So we can run through what this summed plot looks like, sort of a time view of each of these events and how these reconstructions look. And it kind of verifies this idea that, okay, we see that we have a pretty accurate matchup of what the shapes of these looked like, where now the reconstruction is this orange line. The shape is pretty well matched, but there's some noise that is being left out here, and so we have some reconstruction loss. What we can check now is how much data we have after with this autoencoder. So again, the entire point of this is we have now an encoder that passes data from an input into a latent representation. And this latent representation, we're saying now, has all the information that the original input data had. And so we can use that as the data representation itself. So with this 128 latent dimensions that I specified, we now have a data size that is less than or about 100th of a gigabyte. And again, if you remember earlier, we had 1.79 gigabytes for the full size of the 10,000 events. These are the same 10,000 events, just now passed through this encoder. We can take a look also at what these encodings look like themselves. And you can see that this, well, it doesn't make much sense in that there's no relationship between, I mean, these are corresponding plots to what we had here, but there's really no rhyme or reason to why this cluster of pixels is light here and darker here, and this one's really dark here. The reason for that kind of gets at this larger idea in machine learning that is actually one of the drawbacks where a lot of neural networks operate as quote unquote black boxes, where we don't know what is happening inside this network, even though we know that the output looks good. What's going on in here, including what the latent representation itself, which is what this plot is visualizing, actually looks like, it doesn't make much sense. And there's not a lot we can do to interpret why the neural network chose to do this arrangement of coloring for these events. And however, we can check if this representation does in fact contain the data that we're hoping that it does. Specifically, we can go back to this model that predicted delta mu, which you should have run back up here, where we're trying to predict the time difference between the two scatters in each of these multi-scatter events. And we can now train this neural network on the encoded data, on the smaller data representation, to see if we get similar performance to what we did before. And so running this block, it'll do the same training process, but now with the encoded data. And you should be able to see here that, unlike before where it ran in 80 something seconds, it runs now in 4.12 seconds, achieving actually slightly less testing loss here compared to before. And again, importantly, in just 4 seconds. We can plot the performance comparison between the model trained on the raw data and the compressed data, and you can see again that the performance is pretty comparable, if not even a little bit better on the right side when we're using the compressed data. And so now we can see sort of a full summary of what we've achieved here, right? So we've taken this 1.7 gigabyte data and translated it into just 5 megabytes of data, which is a 350 times reduction in the size of the data. We've taken the training time from 72 seconds to 4 seconds, which is a 17 times reduction. And we've decreased the loss achieved in 8 epochs of training, which is this 1.07 times reduction. And so these are all big wins. a dramatic reduction in the data size as a result from a dramatic reduction in the amount of training time that we need. And so as a result, let's see, okay, what can we do with this same amount of training time that we used for the original network on the raw data, holding that constant, saying, okay, let's try to use all 72 seconds to train this model. How well can we do? Of course, we can do a lot more epochs, which again, this is the amount of time that it's running through the 10,000 events in training. We can do a lot more because we have now 72 seconds. And we can see that, okay, the loss here is descending far lower in the same amount of time than the model trained on raw data was. So after 140 epochs here, we can see, okay, this didn't even take 70 seconds, but we've achieved a testing loss of 80 nanoseconds squared. And again, this is with mean squared error and using this delta mu prediction task. We can plot again what this comparison looks like on our scatter plot. And now we have a pretty strong fit to this true delta mu equals predicted delta mu line with the same amount of training time, actually less training time, and a smaller model. So these are like the kind of final two figures, like what have we achieved here? Okay, we've reduced the delta mu testing loss with this encoded data using our autoencoder, and we've also created a model that has relatively low, and again, I'm kind of using this relatively loosely here, liberally, because it's hard to determine. I mean, we can visually say that the reconstruction looks good, but we kind of need these auxiliary tasks to verify that, okay, our encoded representation is good. So now it's probably a good time to stop for questions, if there are any, or if you would like to. It's also a good time to, after running this, revisit the original model that you've made, try to make modifications to either the latent size, that is the size of the encoded representation, or other parts of the model to try to achieve better performance in each of these categories. There should also be a submission form for on Google Forms for you to record these numbers and this plot. So if you'd like to do that alongside your name, we're going to take a look at those a little bit later. But again, go back, see if you can improve your model, and I'll check for questions here.
Shawn may also want to help you,
Right.
because I know it's difficult when you're lecturing with the screen and everything to be able to read the questions. Shawn, do you want to help with those, or I can do it if you can't?
Yes, and if anybody has questions also, excuse me, on the not just this, but also on the physics as well. These are also very important and interesting questions to ask. So please don't feel. So a couple of people asked them, but please don't be afraid to ask physics questions as well.
So there are a number.
And
Shawn, do you want to help deal with those? Help Woody, because it is difficult for Woody because he's got his.
Yes, yes, I can start typing, and Woody can walk through some things if he likes.
What I meant is you were going to read them out for either.
Oh, I'm sorry. Yes, yes, of course, of course. Sorry, let me switch to the open tab. Um, are you familiar with sparse autoencoders? I've come across this while studying interpretability.
yeah, so sparse autoencoders, there's a lot of ways to improve the training efficiency, overfitting of autoencoders. Like one of the biggest problems of autoencoders is that they overfit. And if you dive into this a little bit more, you can see that actually even this autoencoder will tend to overfit, especially with this data size. So sparse autoencoders are a way to address some of those problems by basically knocking out some of the intermediary connections within the autoencoder.
Okay, this might have been mentioned, but how are the number of nodes in the central layer decided?
Yeah, so the central layer, meaning this, I assume is a question. This is, again, the latent size, and it's really up to you to decide what this layer size is. It kind of dictates the amount of information that you're willing to concede in your data representation, how much data you're willing to store. And in that, there's a trade-off between how accurate your final reconstruction of the data is, in that if this intermediary layer is larger, then you can get a better reconstruction. And of course, how big your representation, your latent representation is. The smaller it is, being the bigger the reduction in data sizes, the faster you can train models on the encoded data, et cetera. So it's up to you to determine the size of this latent representation. It's a topic of research in a lot of cases and in practical settings. So
Yep. Um, how do we make sure we don't lose important slash relevant information when we use autoencoders? What sort of checks are usually used here?
yeah, I mean that's a really good question. It's kind of quintessential to this entire task of lossy compression, right? What information do we care about? What information can be thrown away? And sort of the simple way is by doing this reconstruction thing. And for different tasks, we can define different reconstruction losses that preserve or that emphasize preserving different qualities of the input data. Here, obviously, with using mean squared error loss, we're really just looking for a pretty even visual match. The fact that we're squaring it is we don't want any extreme misses in the reconstruction. We just want a pretty as accurate visually of a reconstruction as possible. But you can change that reconstruction loss. You can also do these auxiliary tasks of predicting delta mu, or for whatever the task is, use the encoded representation, which we only trained on a reconstruction loss in the autoencoder training to do some other tasks. And so what we've tried to do here with this delta mu task is see, okay, we have this important information that isn't inherently available in our reconstruction loss. Do we still have that information in the data? And again, it's task specific to what that information is that you might want to preserve. But usually it's some combination of these two things that you're trying to use to evaluate whether you have that data.
Okay. Forgive me, I am fairly new to ML, just out of general curiosity. Is it not better to have losses from ML models be unitless, or is that not something that matters as much?
Um, well, it's an interesting question. So you can have some pretty wacky loss functions. The the loss function for a machine learning model is really just the thing that you're optimizing over. And so in a sense, they can be unitless if you're making some customized loss function. Also, if you're depending on the task that you're doing, um, for example, if you're familiar with a classification task, you would use binary cross entropy loss, which has um, sort of a stranger unit that does exist but isn't as interpretable. Um, for physics purposes, we often prefer to have a unit that makes some sense. There's usually something that we're trying to reduce in terms of the like some proximity to an optimal value that we're trying to get when optimizing a model. So we usually stick to unit uh, loss functions with units, but it depends.
Yep. Um, does the compressed data lose information about the actual relationship between the plotted raw data? The raw data looks more parabolic, while the compressed data looks linear.
Um, yeah, so this relationship, so I think you're talking about this, where this kind of looks like a parabola. And really it's more visible down here. This looks pretty linear on the right. So this parabola is actually like, this is the true, like a perfect model would be able to predict this right on this y equals x line. So in that sense, like this graph should be very linear. This parabola-like formation is just this model unable to, in this small delta mu region, distinguish between events particularly well. So it's more so an artifact of the model and not an artifact of the data. Um, so we would consider this to be uh, a better performance in terms of predicting true delta mu.
Okay. If we're choosing visual reconstruction or some auxiliary task to see how true the outputs from the autoencoder is, does it take some sort of bias specifically uh, to the auxiliary task to compress data we're generating, or do autoencoders fundamentally not work that way?
Yes, it does. So uh, like in any in a lot of contexts in machine learning, if you're looking at some number to optimize over, even if it's like a number that is like test loss that you're not directly optimizing over, but you're like looking at it um, to try to decrease it as much as possible, and you're making changes to your network's hyperparameters that are trying to decrease this loss. Um, it's it could very well be the case that you're biasing toward that figure. And in this case, we have this auxiliary task. And so because we're engineering this model to perform as well as possible with respect to the auxiliary task, even though the autoencoder itself can't see it, um, it is possible that we make changes to the autoencoder that preserves some data that is well suited for this task, but maybe for other tasks, it's not well suited. And we've created a biased model in some sense. Um, so yeah, the answer is yes, it can be a biased endeavor. To fight that, it's like it's just a matter of selecting as many tasks as possible, as holistic of an evaluation criteria as possible to try to mitigate any bias that you have toward one specific feature of the data.
What kind of data compression is being used here? How is the dimensionality of the latent space decided? Maybe answer that.
Yeah, so again, this is autoencoders are sort of a data compression method in of itself. It's a lossy data compression method, so we're losing some information, and the reduction of the data size. One of the benefits of the autoencoder is that you can define whatever reduction amount that you want to. And so in this case, with this task, you could probably go to 1,000 times reduction in the data size and still get a pretty good reconstruction at the end. But that's sort of up to you. But it's one of the benefits of using this autoencoder method.
Hey, I'm not seeing any more questions. If people have more questions, please feel free to type them into the Q&A. There's just been a few. I've been trying to keep track of them. Also, physics questions are also valid, good questions to ask. Is there a reason we choose the linear activation function for the latent layer?
Um, well, sort of. When we're choosing this latent layer, this if I can find the diagram here. When we're shooting this latent layer, this is trying to essentially create a multi-dimensional space that our input data is mapping into. And we are placing a constraint on this space already by constraining the dimensionality of it with respect to the input dimensionality. There are other constraints that you can put on this latent space. You can quantize it, meaning that you restrict it to being only integer or non irregular data. Like you can make this representation in different ways so that the ultimately so that the data size is restricted as much as possible. And so the reason we don't use other activation functions typically, like if you were to use like a sigmoid activation function, that would restrict this to 0 to 1 floating point numbers, where the actual size of the data, because we're still using floating point numbers of the same size, like float 32s, the size of the data isn't changed. And so in essence, we're taking advantage of relatively much less of the latent space than we could with like if we just have linear activation and give it the full advantage of having the entire range of floating point numbers. So we can take there's autoencoders called vector quantized variational autoencoders, which take this latent space and map it to discrete vectors, which is often used, but in other ways, often we don't want to restrict the power of this latent space if it doesn't translate to a reduction in the data size itself.
Okay. There are a couple of questions that may be more appropriate for Rick and I, but any one of us three can answer. So aside from data compression, what tasks can we use autoencoders for that are relevant for this experiment? Maybe Rick wants to answer that, but
Yes,
maybe, yeah, go ahead.
well, as you'll have seen from what Shawn and Woody are showing, is that autoencoders are a way of discovering the sort of basis vectors or the best way of describing data. Now, of course, that style of analysis is something that humans naturally do when we're trying to understand physics data that come from experiments. We're trying to look for the most, descriptive or most meaningful, quantitatively meaningful aspects of the data. It's very typical for those of you who've either had a chance to work in in an experiment or read papers about it. You'll see that there's a big emphasis on taking these sort of petabyte levels of data and reducing it to a much smaller representation of numbers for, in this case, each event that adequately gets at the energy of an event or the characteristic of the event. Is it more associated with a conventional electron recoil event? Is it more likely to be a nuclear recoil event that could occur from a dark matter particle? This type of thing. So you can the techniques that Woody and Shawn have been talking about also help us in many cases to better understand what additional representations there may be beyond the ones that we've already discovered through more traditional techniques. So that use of machine learning to supplement or to help inform us better. I mean, one may say that working with humans, one often finds that our ability, should we say, to visualize in our own heads multi-parameter space gets quite difficult, when you have maybe more than sort of 6, 7, it depends how good you are, but 8 free parameters. Trying to actually hold the multi-dimensional parameter space in your head can be quite challenging for most people. And of course, this is an area where, both traditional statistical techniques and, their incarnation now in the form of machine learning can help us with, it is capable often of discovering in multi-parameter space whether, the parameter description has become, or the effective dimensionality has become extremely large. Now, as I hope you got from Woody's, description, of course, this is not a magic bullet. The data, the properties of, you need a large amount of data. If the effects you're looking for are very subtle, you need a large amount of data often to, to be in with a shot of discovering it. If the features are less subtle, then they become apparent in a smaller data set, although of course it's usually pretty apparent that the humans have already discovered this. I mean, even the work that Woody and Shawn have been doing on simulated data, which is inspired here by LUX-ZEPLIN, time projection chamber, which is the type of detector. This sort of simulated data, which is helping people understand better the way real data behaves. The performance of these systems is, initially can often be comparable to what humans have already achieved. What you can find is that some of the more subtle aspects of it, and especially as Woody demonstrated, the defining of a economical representation, an economical in terms of data storage and in terms of processing, that's something that the autoencoders are incredibly good at, and is a major benefit, because even if we then use the output of the autoencoders, the compressed relationship, as the unit for humans to then work with, the fact that you've shrunk the data so significantly substantially improves your ability as an analyst, as a human, to work with the data, because it will process and you will analyze it so much faster because it's been reduced in its representation. So that is another major, because we, as Woody and Shawn said, petabyte levels of data. I don't know those of you who have sort of dealt with data at that sort of level of volume. While the financial cost of getting a petabyte of data, in terms of disk drive, say, or similar, has come down very substantially every year, and is now, you can build arrays to store that kind of data at tens of thousands of dollars, which is quite incredible. But the human's ability to actually sift through petabytes, you need to look for techniques to shrink that data in a very effective and efficient way. And this autoencoder approach, of discovery of the right way to shrink data is proving, I think, enormously successful, not just in dark matter experiments, but in a whole range of potential experiments that have this sort of large amount of data.
Okay.
Yeah.
Thank you. What other kinds of data compression methods are commonly used for these large data sets?
Yeah, so people use a combination of lossy and lossless data compression methods. There are a lot of lossless data compression methods that people have come up with, especially within the field of image compression and video compression. There's quite a lot of research done on lossy compression of video and image data. And that work is quite interesting and actually shockingly pretty translatable to a lot of other types of data. And so if you've ever seen like JPEG or PNG, these are all compression methods that have been performed on image data. If you ever uploaded a video to YouTube, that video in and of itself might be quite large, but YouTube is able to compress it sometimes by a factor of 10 or many multiples, it's able to compress the video through various techniques, such as but not limited to, matching pixel values, or describing like adjacent pixel values as with many fewer numbers, or um, reducing the number of available colors that are used at any given frame. So these are sort of demonstrative of a lot of different techniques that can be used for large data formats, not just images and videos. But autoencoders have been used in a lot of contexts, and there's many different flavors of autoencoders now, such as variational autoencoders, which are in this notebook, which I can talk a little bit about later, or vector quantized autoencoders, sparse autoencoders that are used as a machine learning approach to that data compression.
Yep. Okay, thank you. If S1 pulse is too weak, can the signal travel to S2 if it originates at a far away distance from the PMT? If I understand this question correctly, it's not exactly the correct way to think of it. It's that for each scatter event, there should be two signals, the S1, which is the prompt release of UV photons, and the S2, which is due to the drifted electrons. So each scatter produces these S1 and S2 signals. S1 happens first, S2 happens second. It's not that S1 travels to S2, it's just that S1 and S2 are displaced in time. That's all.
Could I add something?
Definitely.
I just wanted to make it clear what you've seen in this notebook case study is a simulated style of event. It's based on signals that we see in time projection chambers of the kind that LZ uses. And in particular, this type of event is known as the S2 event, as was said. It's the second of the two components of a typical signal. But this is a simulated event, and we've made simplifications both in terms of the time domain and particularly the spatial pattern in order to make it a completely self-contained, easier and accessible for somebody who's wanting to understand autoencoders. There is a lot of material under the LUX-ZEPLIN published papers. Archive, ARXIV, is always a great place to start for experimental and actually theoretical papers as well in dark matter and high energy and particle physics and astrophysics papers. But LUX-ZEPLIN, which is just, by the way, somebody did ask, we didn't specifically address this, but somebody asked about this, where acronyms come from. The term LUX, LUX, was an experiment that is the large underground xenon experiment, LUX, which was carried out prior to this new incarnation, which is LUX-ZEPLIN. And actually the term Zeppelin, spelt ZEPLIN, is again an acronym of an earlier experiment. I think as somebody caught in one of the Q&A sessions, that it is there are a number of internal jokes, should we say, associated with these styles of acronyms, but it's always useful to have some kind of title or acronym or name for an experiment that makes it readily identifiable. And we use this LUX-ZEPLIN tag as the name of the current incarnation of the experiment.
Yep. How can we ensure that the latent space representation of the original data distribution is not biased towards certain data points? For example, latent space's data distribution doesn't contain outliers.
Yeah, that's actually a really good question. So as I mentioned earlier, there's no constraint that we're placing, especially again with the linear activation function, there's no constraint that we're placing on this latent vector space that we have in the intermediary representation. And so not only can that be not interpretable, it can also not really make sense and actually cause a lot of the biasing issues that you see in autoencoders themselves. So one of the remedies that we have to that is introducing this variational autoencoder, this concept of variational autoencoder. And what a variational autoencoder does differently is instead of considering each sample in the data as a separate discrete element of the latent space, it instead considers each sample as a sample from a latent distribution. Specifically, that latent distribution, it's trying to model internally Gaussian distributions in the latent space. So instead of producing a single vector for each element, each event that's passed to the encoder, it passes through a vector associated with a mean and a vector associated with a standard deviation, or actually specifically the log of the variance of this Gaussian distribution. And alongside that, there's this concept of a KL loss, a Kullback-Leibler divergence loss, which takes the output for these latent representations, or these latent distributions, and restricts them to be Gaussian-like. And so what ends up happening is you have now models that map samples to Gaussian latent distributions, and then to reconstruct those, they sample from whatever Gaussian distribution is defined by this sample's input. And so that does a couple things. That allows us for noisy input, for input that may have noise that's unrelated to the distribution, to the actual sample in the distribution. It allows us to remove that noise, or at least not consider that noise when we're translating it through this latent space, instead of maybe assigning it a discrete point value in the latent space that's kind of meaningless. And in this experiment, we actually have quite a bit of that noise. We have these variations which aren't actually tied to the event themselves. This is actually quite literally just a combination of Gaussian and Poisson noise that's generated when you scintillate light through, or during the scintillation of light through the electrons that are percolating through this chamber. They come up randomly and scatter light randomly. And so using a vanilla autoencoder, we are forced to translate all of these discrete samples into the latent space one-to-one. Whereas here in the variational autoencoder, we can map it into distributions, and then those distribution samples will be noisy themselves, or will at least learn that the noise in the input isn't actually part of the data, a meaningful part of the data. Just because, again, this noise is impossible to reliably reproduce. And in some sense, we don't really care about reproducing it because it doesn't convey any physics information. So that's one kind of way that we can constrain the latent space, and it happens to be quite useful to fixing this problem that's very common in autoencoders of overfitting to input data, to noise in the input data. So again, if you have time, I would recommend going through this variation autoencoder section. There's just a little bit in this section to fill in. It's pretty similar to the autoencoder section itself. And running through that, you'll kind of be able to see alongside this small bit of math here about how we exactly draw those samples, and also how we backpropagate with this element of randomness. It's all quite interesting, and it is a big step that machine learning researchers have found in this task of compressing data with autoencoders.
Yep. I don't see any more open questions. I'll give, okay. Which parameter spaces will be constrained in the WIMP hypothesis of dark matter in case of non-detection or real event per year? Maybe I can give a quick answer, and Rick can compound on that if he likes. But usually you constrain the cross-section for different hypothesized WIMP masses. So the cross section has units of area square, units of area. So for example, centimeter squared is what you'll often see, and it's you can think of it as kind of the area the particle needs to hit in order to be detected. It's sort of a proxy for a probability of interaction. So it's the the um, the detector constrains this quantity of the cross section for various WIMP masses. And I don't know, Rick, if you want to add to that.
Yes, Shawn, when he opened with the motivating science, we have very real direct evidence that a third of the mass energy of our universe is matter. But as we've discovered over the last 100 years, that matter component is not the matter that you and I are made of. The protons, neutrons, electrons of conventional matter can only be at most, say, 4.5% of the composition of the universe. So we have got to figure out what the rest of the matter is. And because it doesn't interact with electromagnetic signals, which is traditional astronomy, we call it dark matter. So, as Shawn said, we've got to somehow quantify the probability of this additional dark matter interacting with conventional matter. Now, we know it does so gravitationally, but gravity is an incredibly weak force, and experimentally in the laboratory does not really present a way to to probe the properties of the dark matter. We can astrophysically use the gravitational interaction, but we'd like to know more about the dark matter beyond just its gravitational behavior. So we are attempting, for instance, to get the direct interaction of a dark matter particle as it flies through us and flies through the Earth, because these dark matter particles are the dominant particles in our galaxy. We're hoping for an interaction, and as Shawn said, that's if you like a probability or a cross section. So we have an enormous number of theoretical models for the dark matter particles. There are models of the dark matter particles that certainly solve the abundance. You get the right amount of abundance of this dark matter particle through mechanisms in the early universe. But given the data we have at the moment, our theoretical models do not make an exact prediction of the probability of it interacting with conventional matter through some kind of scattering mechanism. So in doing the experimental searches, we have to allow for a range of possible cross sections. Now, in the time, I've been working on the dark matter problem, we have tested dark matter particle hypotheses which have had cross sections which have varied in range by more than a factor of 1 million. We started with the types of models that had cross sections that were sort of far more similar to those that you see in, for instance, neutrino interactions, if we assumed that the dark matter was just heavy neutrinos. But we would have seen them. We would have seen them actually back in the 1980s, with the experiments we did then. It turns out that nature didn't this extra dark matter is not of a sort of regular type of heavy Dirac neutrino form. We have done the same thing repeatedly in terms of forming theoretical models that fit all of the current observational constraints for particle dark matter. And we've attempted to look for them. As things stand at the moment, I think it's reasonable to say that we don't have any direct measurement of a particle dark matter that helps us narrow exactly what the properties of it are. We've tried to create those particles in particle accelerators. We've tried to look for the signature of those particles from their annihilation in the in gravitational concentrations in our galaxy. We have tried to look for direct interactions. But what you have to recognize is that nature's when we construct these experiments, we're limited by the sort of physicality, the necessary our ability to sort of construct experiments of appropriate sort of sizes. And when I was a graduate student, we were constructing experiments that had targets the size of your sort of thumbnail. We're now constructing experiments that are, have a linear size target, which is, measured in meters, many meters. So, and weigh 10 tons. So we have scaled up the sensitivity of these experiments, but in terms of the amount of parameter space, possible parameter space that we've been able to probe, we are unfortunately limited. But we continue to do it because that's how scientific discovery works. And if you actually look back at the way the history of scientific discovery works, we all know about the successes, but one may sometimes be forgiven for not fully recognizing that between the models that turned out to be the successful ones, you have to eliminate a lot of very unsuccessful models. And the history books don't always record those because, quite rightly, we tend to focus on the models that are working today. So dark matter is a very live problem. We're right in the middle of it, pun intended. We're right in the middle of trying to solve this challenge, and it means we are testing models, and we've eliminated a large number of models, and we continue to test new models for it. And we do it not just through the direct detection techniques that were outlined in this module today, but through a whole slew of other possible techniques. And the very nature of scientific research is most experiments get negative results. That's what we do every so often, and not always in a way that's predictable. With research, you get a positive result from an area of research. That's really for all of those who are starting your careers in research, you're going to do a lot of experiments that don't turn out necessarily to see anything directly, that they will disprove a hypothesis, but you keep moving forward. That's it. That is the type of the definition of the way scientific research works, because we don't know what the answer is a priori in advance. You have a well-motivated hypothesis, you construct an experiment in order to test it, and then you try to make sure that those results can be clearly interpreted, and that influences what we do next. And this is the kind of work we're approaching to understanding our universe composition. But again, pun intended, the universe is an incredibly big place, and the scale of the challenges that we have right now to understand in detail what dark matter and dark energy there's just no guarantee we make the discovery tomorrow or indeed next year. We just don't know when we're going to make the discovery that actually helps resolve exactly what dark matter and dark energy are. But for those of you who have gone back and looked at scientific, what I suppose are history books now, you'll see that our model of our universe, even in the last 100 years, has evolved very significantly, both in terms of scale and in terms of the accuracy with which we think we understand it. We now know the age of the universe, at the sort of percent level, which even when I was a graduate student, that number was uncertain. At the level of nearly a factor of 2. So we've improved numbers like that enormously. We've improved our understanding of composition. What we have still, that we remain, this challenge of the dark sector, the dark matter and the dark energy, are huge questions that we still need to try to address and get to a solution. But we don't yet have data from any experiment that I think definitively identifies what the actual composition, or sort of theoretically, the theoretical model that actually best describes, what that dark matter is, or what the dark energy property actually is. Anyway, I'll stop there. Sorry, this is really a machine learning discussion, but for those of you who are interested, please do read around these issues. There are many potential sources if you just start Googling or looking at the archive papers, for those of you who want to look at the science papers.
Okay. Just to There's a question that just follows that. The dark matter experiments currently happening are testing the WIMP theory or other theories as well. So there's another noble liquid experiment called xenon, which also is similar to this one, and it looks for WIMPs. But there are also other experiments that you can look for dark matter in. There you can look for dark matter in collider experiments, such as the Bell 2 experiment in Japan. It looks for many dark matter experiment models, such as E plus E minus goes to a dark photon in dark Higgs through a process called Higgs Strahlung, where the dark photon decays to leptons. That's one way. There's also indirect ways to search for dark matter, such as the alpha magnetic spectrometer mounted on the International Space Station. It measures astrophysical phenomena, and it checks against those phenomena against models that either have dark matter or just standard astrophysical models. That's sort of an indirect way. And there for from specifically non-wimpy searches, there's, like I said in the beginning, there's a candidate called the Axion. There's an experiment called the Axion Dark Matter Experiment called or ADMX, which searches for this. And there are other things in the planning stage. So there are other theories that are being tested as well. The other next question is, assuming the data is collected of a certain event that is happening in the universe, how can we learn about the dynamics of the event that is happening at that place using AI models like neural operators learning? If possible, how? If not, then what are the possible challenges and direction to tackle this problem? So maybe Rick can pick up the question of how we learn about the dynamics of the event that is happening in the detector.
You know, questions you're getting at the heart of any model you might come up for explaining the dark matter component of the universe needs to make predictions, and those indeed may be dynamical predictions, specific velocity distribution of the material, specific mass, composition, interaction strength with conventional material. That's getting to the heart of the way scientific hypothesis building works. You have to make predictions that are testable experimentally. That's how the scientific process works. There is a challenge associated with our introduction of machine learning techniques into this process because, as from a physics perspective, we have to be careful not to relegate aspects of the experiment to, if you like, a hidden black box kind of dark box. And in this case, I mean dark in the sense of you can't see inside it. There has to be a clear chain of logic and hypothesis testing. So there are going to be moments when we're developing techniques. Woody's and Shawn have been showing here techniques for extracting the most apparently salient aspects of events, but we have to do so in a way that we make sure that we understand what information we're keeping, what information we're throwing away. Doesn't mean we don't try these techniques, but we have to go back and make sure that we understand why the optimizations that are described here with the autoencoder have gone the way they have. If as an experimentalist, you're going to take this huge amount of data and end up concluding and indeed publishing papers to say that you feel you have, you feel that you have evidence for dark matter events, you will, during the refereeing process, during the Q&A process that happens for any scientific, result discussion, you need to be ready to clearly describe every stage in your analysis. And we are going to see the use of ML AI techniques more and more in experiments, but as scientists, we are going to have to be able to very clearly describe and explain how the ML the statistics associated with the ML machine learning, how that was applied and how it, should we say, constrained and sifted the data. Especially for these types of searches where you're going to end up pointing to a limited number of events in your detection instrument and saying we strongly suggest that these events are consistent with a dark matter signal, you are going to need to really understand all the way from beginning to end exactly how your processing worked. And so we certainly will use these techniques, but from a physics perspective, we're going to have to make sure we understand how these techniques actually acted on the data. We can't at any stage say, well, there's a physics cartoon that's existed, I think, for decades now, which is somebody scribbling on a board a theory, and then it says, and magic occurs here just before they write the QED, the answer. We're not allowed ever to resort to magic occurs here in scientific discovery and verification of hypotheses and differentiation of hypotheses that are good and ones that have failed. We have to have complete transparency on this. So that is going to be one of the challenges associated with use of machine learning and AI techniques within many disciplines of science. And in physics, we've over the last 200-300 years, you've seen a very successful technique development of a scientific method, which has proved to be a very substantial and stable basis for hierarchical logic and deduction and hypothesis testing. And we probably, well, it's not to say that there may not be a new technique that, should we say, takes over, but this the business of having clear logic chains and clear clear hypothesis testing, I think, is one that we need to depend on. Well, as Wittgenstein was fond of saying, he often talked about pulling up the ladders from earlier logic. I'm not sure we have quite that luxury within some of the way the physics works. We've got to be very careful about appearing to no longer understand the basis on which our conclusions have been made. We have to be able to trace them all the way back. And that is a successful technique for ensuring that your scientific deduction and reproducibility of experimental results is well established. Anyway, again, bordering on philosophical here, but I just want to make it's a useful opportunity to make that point for all of those you who are working on applying machine learning and artificial intelligence within science. Go for it, but do recognize that we must understand these techniques at the detail level. As I'm sure you may also have frankly, the discoveries, the very meaningful discoveries you're going to make in AI and machine learning and your ability to drive it forward will also come from you having a very detailed understanding of these processes. So don't, for instance, in providing all these workbooks we have, we wanted to show you what was possible, but please do dig into them. Don't just execute them and think job done. I understand autoencoders. The work that Woody and Shawn have shown here came from multiple years of discussion, optimization. Everybody involved has learned a great deal about the way in which what works and what doesn't work. And if you want to be at the vanguard of future work, it will come not because you're the fastest person to execute a new piece of code, but because you actually have spent time understanding in detail how the code is made. If you read what is written by a number of the current leaders within the AI and ML field, you will rapidly realize just how well and at a detailed level they understand what they're doing. It's not that they were first because they were fast on their feet or had the largest machine, although it does turn out that, as you can see, processing power is you do have to align that, but it is also strongly dependent on you having a fundamental understanding of how these techniques work. So I would advocate, and I hope our modules that we have been demonstrating, the one that Woody and Shawn put together, the other previous modules 1 through 5, have all been designed to help you get a detailed understanding of how the various machine learning techniques are put together, so you can then take them apart and understand them. Anyway, sorry, I'll stop there.
Okay, thank you. I don't see any other open questions. I'll just wait for a few seconds. But if not, then we can close out the session.
Yeah, I'd just like to thank Shawn and Woody again for an outstanding case study. I obviously they've had to simplify things enormously. This was inspired by the work we do on dark matter, but they've simulated, sort of idealized or simplified, rather not idealized, simplified event properties. But it means, I think, the material is as a consequence nicely accessible, and I would strongly urge those of you who have been taking an interest in this work to use this workbook to go back and see how it may apply in areas that you're interested in. It's very, very good demonstration. Thank you to both of you for working so hard on this.
Yep, and thank you, Rick, as well, for being here and helping to answer questions with your expertise. So I don't see any other open questions popping up. So I'm going to go ahead and declare the session closed, and thank you everybody for attending. I hope you got something out of it.